That Spotify API is really irritating me. I think it's the library I'm using to send requests, but I got debugging to do, and it's frustrating. Testing's hard enough, as you're all finding out. Testing's tough. When you're testing something with timing involved, it gets way, way trickier too. It's hard to test things like this. All right, so let's continue our conversation with linked lists. That's not an excuse. I should be able to do it anyway, but something, I think it's the library I'm using. It's just not sending the requests sometimes. And then sometimes Spotify is just denying the requests too. So I think it's on both ends, which is just all kinds of fun. All right, so let's continue our conversation about linked lists. And first, as promised, we're going to talk about generics. So generics, well, first of all, without generics, this is the code that we saw last time on Monday. We saw a linked list node class, and I called it linked list node int. This is a linked list node that can only store ints. The value has to be int. It's hard-coded to int. And that's great and all, but what if we want to store literally anything else, anything that's not an int? How are we going to do that? Because array lists can do that. Why can't we? I want to do as much as an array list can do. I want to do as much as a hash map can do. With an array list, we'll create an array list and specify what type we want to store in the array list. This is what I want my linked list to do. So let's do exactly that. Let's change this code around. Here's the code that's going to do exactly that. And then we'll break this apart and see what's going on. So this is going to replace that int with a generic type, which I sometimes call a type parameter. That's what it's called in some other languages. I believe C++ calls them templates, if I'm remembering right. Java calls them generics. I like to call them type parameters. I think it's the most descriptive name for them, and that can span any language, no matter what language I'm talking about. So if I say type parameter or generic, I mean those interchangeably. With generics, we're going to create a generic parameter list, I guess. I always call this a type parameter list. I don't know. But a type parameter list, there's another parameter list that we're going to need to satisfy when we create objects of this type or variables of this type. And the syntax is create that list right here after the name of the class using angle brackets. And that's why we use angle brackets for our type parameter, or I guess type argument list in array list and hash map. We're going to use this angle bracket syntax to mean generics in Java. So this is saying this class is going to take a generic type, and then I'm going to name it whatever I want to name it. Generally, T here is what I called my generic type. This can be any variable name, and Java will still compile your code. By convention, just as human developers just kind of agreed, by convention, we'll use a single capital letter for these variable names, and then when you see a single capital letter anywhere in code, your alarm bell should be ringing that that is a generic type or a type parameter. It's a type that could be any type, but not one specific type. It could be any type, and it can be different for each run of the code. So I use T here for type. You'll see often A used as a type parameter. If you don't want your variable to mean anything, you just start at the beginning of the alphabet. Start with A. If you need a second one, you use B. If you look at the hash map code, the type parameters are K and V for key and value, which makes sense. Even though we're only using single variables, we can still be a little bit descriptive. K and V, I think that's perfectly descriptive in a hash map. But these can be any variable name, and I say that more as a caution. I'll talk about once I introduce what these things even are. Whenever we need a variable of the type, of the generic type, we're going to use that variable name. I'm going to use T. So I have a variable named value of type T. I don't even know what T is, but I know value is going to be a variable, or a value, I guess, of type T. And val, this is going to be a variable of type T. I just use T in place of what I would have the type being. So this used to be int when we were hard-coded to int. Now we're using generics. This is going to be T, which can be any type, asterisk, except primitive types. Can be any non-primitive type. And we can forward these types to our other type parameters or other generics. So I need a variable that takes a generic type, I need two of them, I can just jam T in there. So I'm saying I don't know what T is, but I need a reference to a linked list node of type T, and I'm going to forward that type parameter to the next node, which is enforcing that every node in this linked list has to have the same type. So I have a linked list node of type T, which creates a linked list of type T, and that linked list can only store values of type T. Now we could, if we wanted to code this differently, we could have next not be T. We could have choose a new letter and have a different type parameter throughout our code and have a type parameter list. We could do some strange things like that, which would be functional, but not necessarily what we want. It doesn't give us the nice functionality like we have in Python and JavaScript, where we can have a linked list with a whole bunch of different types in it, because we still don't know anything about those types, so the compiler's not going to let us do anything special with those types. So we're going to stick with the Java thing of our linked list can only store a single type. And then when we create our linked list node, we're going to specify the type parameter, or I guess this would be the type argument list, to specify the value of T. T is a type, so we're going to give it a type. We're going to say integer, and effectively for this linked list node, or rather this linked list node object that we're creating, T is effectively integer. Every instance of T is effectively replaced with integer. It is not literally replaced with integer. So do not do this in your code. Go to the linked list node class, delete T, and type in rating, because you need a linked list of ratings for task 3. Do not change T to rating. That does not do anything. Doesn't do anything. But every semester I do see that in a lot of office hours questions, a lot of Piazza posts. Don't change T. That is a variable name, which means if you change T to rating, rating's still a valid variable name, so it looks like you have a linked list of ratings, but no, you have a linked list of a generic type, and you happen to name your generic type, that variable, you happen to name it rating, which has zero effect on your program. You do not have a linked list of ratings at that point. So don't make that mistake. It's an easy mistake to make, to be honest. But don't change the linked list node class. My caution there is you have the linked list node class. It's in ratings.datastructures. It's given in the handout code. It's already in your project. Don't change that class at all. Or rather, you don't have to change that class. If you want to add helper methods to it, by all means, go for it. Just don't call those helper methods, if you are going to do that, don't call those helper methods from your tests, because my solutions won't have those helper methods. So just a word of caution if that's what you're doing. But don't change that class unless you have a good reason to, because it's going to not even necessarily break things, but it will not really do what you want it to do. Instead, what you're doing in your song class, where you need a linked list of ratings, create a linked list node of ratings. When you create the object, that's when you specify what the type should be for the generic type. So that's when you specify it. Technically, you specify it right here, but Java does let us do this shorthand, just like array list, just like hash map. Same thing with our linked list. Java doesn't see a type parameter here. Really, we should have integer right here to say create a new linked list node with integer as the generic type T. But Java does let us shorthand this, since it'll look at the variable that we're assigning to it, and it'll look at the type of this value, and it'll say, sure looks like T is integer. I'm just going to assume T is integer. And then it'll kind of fill in integer right here for us. But integer, we're specifying it when we create the object. And then this linked list that we have a reference to, this linked list node, T is effectively integer. So you create a new linked list node of rating, T is effectively rating. Don't change the variable name T to rating, doesn't do anything. It just makes it look right without being right. So my word of caution, I saw that a lot in office hours, so I'm hoping I can scream about that in lecture enough that I don't see it as much in office hours. Hopefully save y'all some time on that one, because it's a frustrating mistake. It takes a while to find. You almost have to go to office hours to catch that one. And we can change this parameter to anything we want. If we want the generic type to be string, we just change that to string. We give this linked list strings. We now have a linked list of strings. We didn't have to change the linked list node code at all to go from ints to strings, from integers to strings. We didn't have to change the code at all because we're coded to a generic type T, and we can have that T be any non-primitive type that we want. So we write this code one time, and we use it for any type that we want. Just like when the Java devs, when they wrote the ArrayList class, they don't know what you're going to use that class for. And you can even use that class. You can create an array list of some type that you wrote that the Java devs had no idea would ever exist. And it'll still work. It's because it works with generic types. You write your data structure code one time and have it work for any type by using generics. Very powerful, very flexible concept. Okay, any questions about generics? Why do we need to write T when we're defining the class? This is how Java works, I guess. I don't have a great answer for you, but that's just where we put our, like right here is like the parameter list. This is our, what I always refer to as the type parameter list, but I guess it's the generic list in Java would be the name of it. But this is your type parameter list. If I don't have this right here, I can't use T anywhere in my class. But once I have this parameter list, then I can use that parameter all throughout my code. But it has to be up here to say, hey, Java, this class takes a generic type. When you're meant to use linked list versus linked list node, when are you meant to use linked list versus linked list node? We'll always use linked list node. But this variable first, it's of type linked list node, but just colloquially, I would refer to this as a linked list. This stores a linked list because it stores a linked list node, which happens to be representing the head of a linked list. So I just call it a linked list. We never use the type linked list, at least in this class. Even the type linked list, any built-in linked list in any language, if you look at the code, if you crack it open, all it's storing is the reference to a node. That's all it actually does. It's just a wrapper class to give you some extra functionality around that. Yeah.
So using a generic, you can use the value variable for like more than one situation.
Yeah. Yeah. So if I create a linked list node of string, value is effectively type string. If I create a linked list node of integer, value is effectively integer. If I create a linked list node of array list of hash map of string to integer, then value is effectively array list of hash map of string to integer. I can put any type that I want there. So I have one class, and each object can have different generic types by specifying what T should be when we create that object. Yeah. Why do you always want to do that? I even mentioned explicitly in lecture just because I knew you'd ask. Why do you want to mix values in your linked list? I mean, you could, but you wouldn't be able to do it with this class, but you can. If you mangle this up and change it a bit, you could have linked list node int, then string. You'd have to change this code, though. What? Why? What's that? If we significantly change the code, we could do it here. With this code, because each linked list node of type T has to reference a linked list node of type T. So the types have to be the same the way this code is written. But generally, in Java, we don't want to mix types, unless those types are related, but that's going to be polymorphism way down the road. Yeah. If you're coming from Python, yeah, it is a constraint. But there are good reasons for it, so the compiler can find our errors before they turn into runtime errors. Because in Python, you're just assuming that the types at each position in a list, and if you're wrong, Python doesn't help you out at all. It just gets to the point where you're wrong and crashes. The reason why we like strong typing, like in Java, is especially when we have very large programs, which is the theme of the course. We have a very large program, so you got 1 million lines of code, which isn't even a lot on an industry. First project you work on in industry, your first job, I wouldn't be surprised if it's 1 million lines of code. You want the compiler checking all that stuff for you, checking all your types before you hit go, and you have a runtime error out of nowhere, and everything just breaks. That's really, really hard to debug. Generally, Python for very large, complex programs isn't very great because of that issue. So we want the types to be enforced by the compiler. That's why we want the types to be enforced by the compiler. For simple scripts under like 1,000 lines, Python's fine. But once we get very large programs, we want this protection. Or else we'd use Python for everything. Honestly, Python's so much easier to code in. All right, so let's talk about some algorithms. So I want to talk about, that's not the right slide. We got to get getters and setters first. So last time, everything I've done with this linked list so far, we did it in the linked list node class, and I just slapped a main method in the linked list node class. That's very restrictive. That's not how we're actually going to use a linked list node from within the class. That doesn't even make sense. Just for the first example, so I'm not throwing too much at you at once, this is a lecture where I'm throwing all the extra details at you, all the extra methods, the type parameters, and all that. So we need some getters and setters, so we can use a linked list node from outside the linked list node class without getters and setters, and we have private instance variables. It's a pretty useless class. It's only helpful if we have a main method inside that class, and I don't know. So let's get our getters and setters in here. And just a quick note, if you don't want somebody doing something to your code, just don't give them a getter or setter. Here I have a notable exclusion of set value. I'm saying I don't want people changing the values of my nodes in my linked list, so I'm just not going to give them a set value method. Easy as that. Now they can't change the values. There's not necessarily a particular reason to do this. For a linked list, if you want to have any properties to the linked list, say you want to maintain a sorted linked list, you wouldn't want to give them a set value method because then anybody can just destroy the sorted order by changing the value of a node. That's what I was thinking when I did this. It also saves room on the slide for what it's worth. But if there's something, in general, if there's something you don't want people doing, don't give them the getter or setter. And then there's 4 methods that I want to go through: size, append, find, methods that we would expect to have on a linked list. Size, just give me how many nodes are in this linked list. Append, add a value to the end of the linked list. Find, give me a reference to the first node that contains the value that I'm looking for. So if there's multiple values, multiple of that value in the list, we're just going to stop when we find the first one. And then the big juicy one, min, this is the one I want to kind of get through these first 3 to get to min. Min is going to mirror what you're expected to do on your homework much more closely than these first 3. So let's jump into size. The easiest of the 3, but not objectively easy. This is our first application of recursion without just having a toy recursion example. I guess we did toString with a linked list last time too. But let's take a look at this. We have size, which is going to return the size of the linked list. What we effectively want to do is count the number of nodes in the linked list. And we're doing this in 2 parts. Our base case is if we're at the end of the list. So remember, these linked lists are null terminated. If next is null, that means we're at the end of the list. This is the last node of the list, or it's a linked list of size 1. If next is null, we effectively have a linked list of size 1, even if that node is being referred to by other nodes and it's part of a much larger list. That node itself is effectively a list of size 1. So it's going to return 1. And if we're not at the end of the list, so hit our else, we're going to ask the next node for its size. And once that next node returns its size, we're going to add 1 to it and return that. So we're adding the 1 to count this node after we get the count from the next node. So the way this looks, and I'm going to start doing abbreviated memory diagrams today and Friday. At this point, I assume that everyone can fill in the details of the memory diagram, but I've got 4 algorithms to go through. There's no way I can do the full memory diagrams for all 4 of them. So we're going to do kind of these abbreviated memory diagrams. Oh, that sounds weird. Diagram of a diagram. So when somebody calls the size method, we have the original caller asking the head of the node. Remember, we only have a reference to the head of the node, the list, or the first node in the linked list. We only have a reference to this guy. So we can't look through the whole thing. I mean, we could with a loop or something, but we only have a reference to this in our variable. So we're going to ask the head of the linked list, hey, what's your size? That node is going to check its next. If it's null, it'll return 1. It's not null here, so it's going to ask the next node. It's going to make this call this.next.size. And since we're calling size through this dot next, in the next stack frame, this is going to be a reference to the next node. So in the next stack frame, this node will be the reference in this. And that node is going to say, well, I'm not the end of the list, so let me ask my next node. So it's going to ask the next node and say, hey, how many nodes are in you as a list? And this node's going to say, I don't know, gee. It's going to look at its next. It's going to see null. So this node doesn't know anything about the rest of the list, but it does know its next is null. So it knows it's the end of the list or the end of a list. It might be the head of the list. It doesn't know. It doesn't care. It doesn't have to care. It's just going to know that next is null, so it's going to return 1. It's going to return the answer 1. This node gets its answer. All these stack frames are sitting here waiting for their answers to come back. Those stack frames are sitting on the stack waiting for control again. This node stack frame gets control again. It gets the answer 1. It's going to pump that up by 1 to count itself because this node is effectively a linked list of size 2, and it's correctly returning 2. In fact, we have on screen here, technically, 4 different linked lists. We have a linked list of size 3 with the values 4, 3, 1, a linked list of size 2 with the values 3, 1, a linked list of size 1 with the value 1, and a linked list of size 0, an empty linked list. If we just have null, that's going to be our way of representing an empty linked list. So if somewhere, and we happen to have a reference to this node, but if we had somewhere else in our program a variable that stores a reference to this node, that variable effectively stores a linked list of size 2, because this is a linked list of size 2. So it's returning the correct answer. It's not returning a partial answer. In this use case, it happens to be, but it is a linked list of size 2. Because if we have a reference to any one of these 4 values, we have a reference to 4 separate linked lists. So we get the answer 2. This node gets control again. The stack frame gets the answer 2, pumps it up by 1, returns 3. And the original caller of the size method gets its final answer 3 and does whatever the rest of the program is going to do with that value. Can you make a linked list of arrays, other linked lists? Sure. Did you say that before I gave my wacky example? The linked lists, let's see if I can remember what I said. A linked list of array lists of hash maps of strings to integers. We can nest these as much as we want. It's one of the powerful things with Java. When I say T can be any type, I mean any type. You can have a linked list of a linked list node of linked list node of linked list node of strings. That's perfectly valid. You can have any type nested as much as you want. Usually we want to avoid that. If you're nested too much, we usually like to create new classes and then encapsulate the details in instance variables to kind of hide the big gross types. But we can have big gross types if we want. So my body is just a really big linked list node. If that's the way you think of yourself, yeah, sure. I ain't gonna stop you. Can I nest myself? Sure. But no primitive types. Yeah, your body is more like a graph. You're like a graph of cells, I guess, if I were to give a data structure analogy for people. Append. Let's get to the next one. So we did prepend effectively last time, but I didn't write a prepend method. I manually prepended to the list. And prepend is a lot easier than append. That's why I started with that one. Prepend, if we have a reference to a node that's the head of a linked list, and we want to prepend a value to it, we're going to create our new linked list node with the new value we want to prepend and set its next equal to the old head of the linked list, and then update our reference that stores the head of the linked list to the new node that we created. That is what we did last time. To append, it's a little bit different because working at the end of the list is a bit harder than working at the beginning of the list because our first goal is to get to the end of the list. To get to the end of the list, we got to call .next, or rather .get next. Oh, I'm not using getters yet, am I? We got to call .next until we get to the end of the list. And we're going to do that with recursion. I forgot to remind of my recursion warning. Recursion, you can do everything with loops, with linked lists. I'll do my abbreviated cautionary tale here. You can do everything with loops. If you do node equals the head of the list, well node not equal null, whatever you want to do with the node, and then node equals node.next or node.getNext, that'll do whatever you want for linked list. I do strongly recommend using recursion to get practice. Well, the recursion is easy. This recursion is 5 lines. This isn't that tough. Even on the homework, the recursion doesn't get too crazy. Deleting a node might get up to, I don't want to give a number because whenever I give a number, students panic if they're even off by 1 of that number, a number of lines. But it won't be too crazy. So get your practice with recursion now, because when you get to trees, you're really going to want recursion. I'll stop it right there. You've heard me say it before. So with append, we need to get to the end of the list first. So if we call append and this.next is null, that's always our way of checking if we're at the end of the list. So if this.next equals null, we are at the end of the list already, and we can insert this value at the end. This.next, instead of being null, we're going to set it equal to a new linked list node with the value we're inserting, and next of null to indicate that that's the new end of the linked list. So we updated the end of the linked list to a new linked list node with the value that we appended. And if we're not at the end of the linked list, we hit our else, and we make our recursive call. This.next.append, so we call append recursively where this is now this.next. So we're effectively moving on to the next node by getting this in the next stack frame equal to a reference to the next node in the linked list, and then forwarding the value that we're inserting. I got ahead of my slides again. All right, so let's see this one in action. We want to add 1 to this, or append 1 to this linked list. We only have a reference to the head of the linked list, so we tell the head of the linked list, hey, I want to add this value. I want to append this value to the end of your list. This node's going to check its next is not null, so it knows that it has no work to do. It's just going to pass the buck on to the next node. It's going to make this recursive call and say, hey, next, this.next, append 1, please. And we get a new stack frame where this is a reference to this node. This node checks its next and sees that it is null. It refers to null, so it says, whoa, I don't know what else is going on ahead of me, but I do know that I'm the end of this list, so it's my job to append this new value. It's going to create a new linked list node, replace its next with a reference to that linked list node. That linked list node has the value that we're inserting and a next of null, so we effectively have a new linked list node with the value 1 appended to the end of it. And notice that this method returns void, so there's no feedback to the original caller that it actually did append that value. We just take it on faith that, hey, that did actually append. And when we're testing our append method, we'll write our tests to call append and then go through the linked list and make sure that all the values are what we expect them to be at the end. But just like add in an array list, it returns void. You just call add on your array list, and you take it on faith that that value actually made it into that array list. So no feedback to the user, returns void. We just call this method for its side effects. Okay, any questions on this so far before we go to find? Yep.
So if this on next is equal to null, then it creates a new linked list node.
Mm-hmm.
So it basically just creates a new linked list node where
Bless you.
whether this top next of that new node is null.
Yeah. Mm-hmm. Can you call it recursive if it's calling the same method in a different object? You know, I do, whenever I go through these slides, it is in the back of my head. Is it technically recursion still? I don't know. I call it recursion because it is calling the same method, but I don't know. If there's some technical documentation that says it's not, then I'm wrong. Can you do live coding in class? I do sometimes. I don't do it nearly as much as Paul does. Paul does it every single lecture. If you're coming from his 115, I assume that's what the comment is meaning. I don't do it nearly as much as he does, but I do it sometimes. We'll get there. I think next Friday is my first live coding. Right? No. With inheritance? I don't remember. Well, if you called these methods from a specific node, I mean, they are called from specific nodes. Like this is a method in the linked list node class, so it has to be called from a specific node, but we usually have a reference to the head of the linked list, so we're calling it through the first node of the linked list. And we have I can kind of use that. Forgot that I can use this in this class. I had the TVs last time. I couldn't use it. I'm not going to use it anyway. So we have an append method. I know I said it in the previous lecture, the previous section on Monday. I don't know if I said it here at all. But if I did, I misspoke and said that I expect you to write the append method. And I forgot that I completely give you the append method. It's even in the handout code for the project. The append method is already there. So that add rating method, just call append for the most part. In the next example, or 2 examples from now, we'll expand on that a little bit. But you do have an append method that you can call anything that's in that class. You can call those methods in your homework when you have to append a rating to the end of a linked list. So let's do find. So we can get to the juicy bits of the min method. So find, we have 2 checks to do, and the order is going to be critically important here. We want to find a value in a linked list. So we're going to check. The first thing we want to check is the value of this node equal to the value I'm looking for? Because if it is, great news. I found what I'm looking for, and I'm going to return a reference to the node where I found that value, which would be this. This stores a reference to that linked list node. We can treat this effectively like a variable. So I'm going to return whatever this resolves to, which is the node that has this value, or the first node that has this value, and return that reference. We often, when we're finding, especially in a linked list, want to return a reference to the node that contains the value, because with linked lists, we usually have to have a reference to the node if we want to manipulate the linked list at all. So if we want to add elements, maybe we want to find where a value is, because we want to insert a node right after the node containing that value. Maybe that's our use case. We want a reference to that node so we can manipulate its .next to be a reference to a new node, and then have the reference of that node be a reference to the old next. Every time I say that, it's a jumble of next. But if we want to insert after this node, we set its next equal to a new node, and that new node's next is equal to whatever that node used to refer to as its next. So we can insert a node in the middle of the list. Something we often want to do with linked lists, so we'll return the node itself, a reference to the node, and not just true. Because usually we would just return true here. Yep, found the thing you're looking for. If we reach the end of the list, that means we did not find this because we reached the end of the list, and importantly, we checked the last node. So this is what I mean by the order is important. If you're in the habit of your first conditional in all your recursive methods is if this.next equals null, then it's our base case and don't do anything. If you say if this.next equals null before you check the value of this node and then return null, that's going to be our way of indicating that we did not find the value in this entire linked list because we reached the end without finding it. Then you'll hit this trap, you'll hit this bug where you're not ever checking the value of the last node of the linked list. This is a very common mistake that I see with linked lists. This is a big office hour question of not checking the last node of a linked list. So make sure before you just check out of your method, before you say, well, this.next is null, so I'm out of here, make sure you are processing that last node. Where this is going to come up is deleting a node in your homework. If the node to be deleted is the last node of a linked list, make sure you're not skipping that one. There is an incorrect solution for that. My tests are going to test for that. And it's a common office hour question. If you come in an office hour and you hear me say, what happens if the value you're trying to delete is the last node of the linked list? This is what I'm talking about. Make sure you check things in the right order. Make sure that last one, and for that matter, make sure the first one's checked as well. Those are the 2 edge cases. Spoilers, I guess. There's incorrect solutions for both of them, but those are the 2 edge cases. What if the value I'm trying to delete is the first value? What if it's the last value? And then if neither of these are true, pass the buck to the next node through recursion. So somebody's looking for the value 3 in this linked list. We ask the head node, the only node we have access to. That node says, well, I don't have the value 3. Maybe my next node does. Do you have the value 3? And just passes the buck. This node says, hold on, I'll check. And it says, oh yeah, I got 3. Here you go. Here's a reference to me. And this node's going to return that reference to the original caller in this case. And give a reference to the node, the first node in this case, containing the value that we're looking for. I keep getting this, like, I've gotten this question 3 times this semester. I usually get it 0 times. I wonder what's going on that I keep getting this question. Bless you. What happens if the end of the linked list, so if the end of the linked list refers to the beginning of the linked list, so this node's next is null, but what if it were a reference to this node instead? You're going infinite. This is never going to be true. So our algorithms are designed to find the end of the list and stop when we get to the end of the list. Our algorithms are going to blow up if we have what's called a cyclical linked list if the last node refers to the first node. It's one of my favorite interview questions, so I wonder if people are just trying to get the answers to my interview questions. How do we show linked lists on stack frames? I did that Monday. We did the whole memory diagram. I only have time for the abbreviated memory diagram this time. And that example that I just did technically wouldn't go infinite, and that example is a bad slide to have up for that. But this one will. I'm looking for 8. This node says, I don't have 8. This node says, I don't have 8. This node says, I don't have 8. Importantly, says, I don't have 8, and then checks if it's the end of the list. Make sure you're processing the last node of the linked list. Sees that its next is null. If this were cyclical, it would go make a recursive call here. It would go in cycles until the stack blows up with a stack overflow. In this case, we do hit the end of the linked list. We have a null terminated list, properly set up one. It says, nope, returns null, returns null, returns null, and the original caller does not get what they're looking for. Not in the linked list. Should we try to stop that in our code of it becoming an infinite? You don't have to add extra logic to like fix that, but you should be careful in the way that you have full control over your linked lists in the song class. Just make sure you don't do anything that's going to break the list. Like you would have to introduce that bug yourself, but I'm not going to give you a linked list. Like when I call set, I forget what I call it, set ratings, where I give you a linked list where I can call that setter in my test, I'm not going to give you a linked list that's cyclical or broken in any way. It's going to be a properly formed linked list. So you don't have to address that in your code, but you shouldn't introduce that bug. Yeah?
So in this example, if we had changed the if and else if statement, like in the last slide, you showed the last node had 1, but even if it had 8 and these were reversed, then it would
Yep.
return 1, right?
Yes. Yeah, so if this was 8 and I had these reversed, then I would hit this dot next equals null. It would say, yep, next is null, return null. And it would never end up checking if it has the value we're looking for. That's the danger that I'm warning about. Yep. Yeah, I should put an asterisk on that one too. Unless you want your code to go infinite. Unless you want your program to blow up. Some people want that. Not judging. Yeah, you won't have a situation where the last node refers to the first node. I like that as an interview question. I wouldn't put it on a homework. Of course, I can't use that question this semester since everybody's asking about it. So I wouldn't put that on an interview either this semester. I like that as an interview question because I don't talk about it in class, and then it gets you to think about the actual structure. Like I get to know if you understand how a linked list works. If I ask that question, you can nail that one. I know you know linked lists, and if you can't, it's a pretty good indicator. And it's something that TAs don't ask. So, but I have to come up with a new question now. So I did cheat a little bit. on the previous example, on the find method, I used the equals method to do this, to check if two things are equal, which is, it's okay, right? But I'm calling this on a variable or on an object of type T. I don't know what T is. It can be literally anything. So the only methods that I can actually call are things like toString and equals are the two most useful ones that every single object has in Java. We can rely on this. We wrote our toString method last time. We were allowed to use toString because everything has that. Actually, we did it with ints anyway, but we could write our toString method. We can find with equals, but we still can't even do this with like ratings, because ratings we didn't write an equals method. The default equals will check if two references refer to the same object on the heap, which is almost always not what we want. So this is very limited. I got away with it because we're looking for ints in those examples. So it worked, but it's very, very, very limited. If we want to do anything besides equality checks, we just can't. We can't do it. So how do we do that? So our next one, min. We want to find the min of doubles. Not every object in Java has a less than operator to be able to find our mins. So how are we going to do this? How are we going to do it? Or more to the point, how are you going to find if a rating has been made by a specific reviewer, which is how you have to delete nodes? So let's change the structure a bit of what we're going to do. Get out of the linked list node class, because I think I mentioned this lecture. If not, I'm doing it right now. You shouldn't change the linked list node class at all. Yeah, I did mention it. You shouldn't change that linked list node class at all. So how are we going to use this? And we're going to use it like this. So this code is meant to mirror your homework, what you're supposed to do in the song class with a linked list node of ratings. For what it's worth, I'm abbreviating linked list node to LL node. It was this line right here was getting way too long and crowded out my words, and I had to make the font really small, so I abbreviated it for the slide. But we have this linked list node, or linked list of doubles, which is meant to mirror the song class. The song is going to have an instance variable that stores a linked list of ratings. So here we have what's the equivalent of the song class, storing a linked list node of doubles here. This would be your linked list node of ratings in the song class. And then we'll initialize that to null to indicate an empty linked list. This is the structure. I shouldn't get any questions about this in office hours. This is how we'll set up the linked list in the song class. You don't go into the linked list node and change that. You don't copy and paste the linked list node code. You use the linked list node class and give it rating as the type, and then you have a linked list of ratings. That's how we do it. Shouldn't get any questions about that. Got a lot of questions about that last semester, so I spoil it now. Because it has nothing to do with your understanding of the structure of linked lists. I just want to get past those logistics so you can get to the juicy part, which is how the hell do I remove a node from this linked list? That's what I'm really testing you on in the homework. All right, so, and this importantly, to create an empty linked list, create a linked list variable. Why would you post that in chat? To create an empty linked list, we're going to create our variable and set it equal to null. Do not create a new linked list node, because once you create a new linked list node, no matter what value you give it, you have a linked list of size 1. What I see a lot of people doing, a lot of students doing, is new linked list node of null to represent their empty linked list. That's not how we do it. That's a linked list of size 1 that stores the value null, which is not what you want at all. And I see it so much, hopefully not this semester because I'm going to shout about it in lecture and wave my arms a bunch. Do not create a new linked list node when you're creating an empty list. We're going to set it equal to null, and then in our code, we're going to check for null to indicate an empty linked list. If numbers is null, I got myself an empty linked list, and if I'm trying to append to the end of an empty linked list, I know what to do here. Now I'm going to set numbers equal to a new linked list node with that value and next of null. Now numbers is a linked list of size 1 with that first value that was added. And then if numbers is not null, Well, we have an append method. We're just going to append. This is what your add rating method should look like, just like this add double, paralleling the homework. Until the min method doesn't as much, but kind of does. But add double, this is your add rating method. Check for null, that's your empty list. Create a new one of size 1. Otherwise, I gave you the append method. It's in the handout code. Just call it. You shouldn't overthink the add rating method. The only way you can mess up on add rating is overthinking it, which I do see. Some people do. Some people will. But don't overthink it. Just follow this template. And hopefully I won't get those office hour questions. I want the office hour questions to be about how the hell do I remove these nodes? How do I delete a node? And then the min method itself. So if the list is empty, we have to have these checks. If the data structure is empty, what do we do? And I'll always have in the homework, if the data structure is empty, do this. You already saw this with the average method in problem set task 1. If it's empty, just return 0, 0 or whatever. For this one, I decided if my linked list is empty, return -1. So this is what you should have in your code if the ratings list is empty. I think I said the average rating should be 0, 0, I believe. If the thing is empty, which means the instance variable stores null, no reference, then return whatever your default should be. I chose -1 here. It doesn't really make sense for this application specifically, but I had to pick something for the example. So I chose -1. Maybe 0, 0 would have made more sense. I don't know. What's the min of an empty data structure? And then we have a bit of an issue. I want to set up my recursion, but my method doesn't take any parameters, so I don't have a good way of passing information to the next stack frame in the recursive call. Whenever this is the case, this is where we like to have helper methods. I'm going to write a helper method that takes any parameters that I want, which for this case, I want the node that I'm currently processing and the total overall min of all the values I've looked at so far. Now, before we had a reference to the node that we're processing, by the way we set up the recursion, we had it in the reference this. So this was always a reference of the node we were processing. Because we were in the linked list node class, we're not in the linked list node class anymore. We're in the linked list of double class. So this is a reference to this class, not a linked list node. So I'm going to add that as a parameter and then use that to set up my recursion. And I have one thing a little messed up. I just got to point this out. This should be double dot positive infinity, not integer dot max value. I got confused when I was writing the code and wrote integer. I forgot I was working with doubles. Integer dot max value doesn't really work here. And then we don't have time to go through the rest of the code. And it's important enough I'll have to pick up on Friday, but we don't have time to go through that in my